Hello everyone, welcome to this new video. So in this today's video, we'll be solving the problem find the string. It's a hard level problem and that it has been asked by Google, and the topic tags of this question are strings, graph, backtracking, data structures and algorithms. Yes, it is a pure backtracking question, and so yes, it is like I would say a hard level question, but once you try to figure out the logic and go through the like intuition, it might be a medium or moderate sort of question, to be honest. So it took a while for me to solve, but at the end of the day I was able to solve this question. All right, so let us go through the question now. Given two integers n and k, the task is to find the string s of minimum length such that it contains all possible strings of size n, okay, size n, as a substring. The characters of the string should be from integers ranging from 0 to k minus 1. So k is the 0 to k minus 1 is the range of the characters. So and you need to form all the like strings of size n, and finally you need to find a string yes, so that you can find all these strings that you have made of size n. All right, so that is the question. So these are some examples 1 and example 2. We'll go through it in brief. So expected time complexity is o of k power n log k. All right, so k power n, this indeed describes that we are actually trying out all the possibilities, and through backtracking, and log k denotes like what are the operations that we are doing per each and every iteration. And space complexity is same, like o of k power n into n. All right, so like same in the sense it's like the intuition is pretty much the blueprint can be formed just by seeing these constants. Yes, we need to do some backtracking sort of stuff, and we need to come to a conclusion. So the constants are n goes up to 4 starting from 1, k goes up to 10 starting from 1, and k power n goes up to 10 power 6. So that is the reason the complexities are in this fashion. And yes, now we are done with like going through the question. Now let us try to understand the question. So this is this is example 1, n equal to 2 and k equal to 2. So what do they mean by n equal to 2 and k equal to 2? N equal to 2 in the sense size of 2, and k equal to 2 in the sense use the characters 0 or 1. So what are all the strings that you can make of size 2 and using 0 1? So I can make 0 0, I can make 0 1, I can make 1 0, I can make 1 1. Is there any other character, any other string possible? No, this is the only string possible. And now try to find a string that has all these strings. Or try to find a big string such that it has all these strings as its substring. Okay, I can make a string like this: 0 0, 0 1, 1 0, 1 1. So I could find 0 0, yes. I could find 0 1, yes. I could find 1 0, yes. I could find 1 1, yes. But why should I repeat this particular point 2 times? They've asked for a substring, so I can even use the same 0 for 0 1 and 0 0. So what I'll do is I'll just write 1 0 instead of here, and here as well I'll write only 1 1. So 1 0 1 1. So in that case, I'm able to find 0 0, yes. I'm able to find 0 1, yes. I'm able to find 1 1, yes. I'm able to find 1 0, yes. So this is done. But still there exists another string that is much more smaller than this. What is that? That is 0 0 1 1 0. Can I find all the strings? Yes, I find 0 0, I find 0 1, I find 1 1, I find 1 0. I could find all of these 4 things, all of these 4 strings. All right, so that is the reason 0 0 1 1 0 is the like the least possible string. There might be another solutions as well, but this is one of them. So this cannot be there cannot be any string much lesser than this. Like this, the length of this string is 5, right? So there cannot exist any string of length 4 such that it has all these particular strings. All right, that is the that is the reason why 0 0 1 1 0 is the answer. So let us delete this. Now come to this particular thing: n equal to 2 and k equal to 3. So k equal to 3 in the sense, what can we infer? Like first, if n equal to 2, so that means size of 2, and k equal to 3, that means I can use the characters 0 1 2. So let us find all the strings that we can form. So I can form 0 0, I can form 0 1, I can form 0 2, I can form 1 0, I can form 1 1, I can form 1 2, I can form 2 0, I can form 2 1, I can form 2 2. All right, now I need to find a string such that it contains all these strings. So all these strings as its substring. Okay, so what is the answer given? That is 0 0 1 0 2 1 1 2 2 0. So can I find all the strings? Yes, I could find 0 0. Let me write it properly. 0 0, yes. I can find 0 1, yes. I can find 0 2, yes. I could find 1 0, yes. I could find 1 1, yes. I could find 1 2, yes. I can find 2 0, yes. I can find 2 1 2 1, yeah. I could find 2 1, yes. I can find 2 2, yes. I could find all of these strings as its substring in this particular string, right? So this is the least possible. I cannot find any other string of length less than this and find all these strings as its substring. I cannot find. So that is the reason this 0 0, this particular thing is the answer. I hope you people understood why this particular string is the answer. Great. So now we'll try to frame the approach. How are we going to come to this conclusion? That how are we able to frame this, or how are we going to find this particular string such that we can find all the strings, all the required strings as its substring. So how do we find that? So here in this case, the n value is 2 and k value is 2. So what can I infer from n equal to 2? The size equal to 2. So size can be 2. The substrings that I'm finding, that I'm going to find in the main string, each of the substring will be of size 2. And k equal to 2 in the sense, I have got a freedom of using the characters 0 and 1. So first and foremost goal is to make sure we find minimum most possible, minimum length, okay, minimum possible length, okay, minimum possible length. How are we going to find this? There are two cases with which we can actually eradicate the duplicacy or reduce the length of the string. How are we? What are the two cases? The first case dilutes to an example. Let us take an example. So what are the substrings that we are going to find? 0, 0, 0, 1, 1, 0, 1, 1. These are the substrings that I'm going to find, right? So will I form a substring like this? Like, will I form a original string like this? 0, 0, 0, 1, 1, 0, 1, 1. Will I form a string like this and say this is the answer? I will not. Why? Because I'm using two zeros here. Why should I use two zeros? What is the necessary of it? I can happily replace these two zeros with 1 0, and I can use this 0 with this 0 and form 0 0 substring. I can use this 0 to frame with to be a part of 1, and I can form 0 1 substring, right? So, I can get two substrings just by using 1 0. Similarly, why should I use two ones? Only one is sufficient. So I can put 0 here, and I can get 0 1, I can get 1 0. So 0 1 is already there, 1 0 we can get, and then 1 1, right? So I must not use like these things for twice if it's not actually needed. If it's not actually needed, I must not use that, all right? Because I'm using two zeros unnecessarily. There is no use of this. So I should only use only one times. Okay, in that fashion we can reduce the length. And what is the other case? Okay, so let us assume, like, again, these are the possible substring that we need to make. Shall I write 0 0 0 0 and like 0 1 1 0 1 1? Will I write the same substring for twice? Will I do it? No, it's unnecessary. It doesn't make any sense. Why will I do this? I cannot write 0 0 for twice. What is the use of that? There's no use, right? There's no practical use of this. We are indeed increasing the length of the string. So we must not do that. So two cases: either you reduce the unnecessary usage. Second, you do not repeat the same possible string for twice. Only once is what maximum that you need to use, so that you can form the minimum most possible pathway. All right, so keep these two things in mind, and now let us frame the approach. So what is the starting thing that you can go with? Starting thing you can go with is 0 0, right? You can go with 0 0. So starting n equal to 2, remember, n equal to 2 and k equal to 2. Okay, start with 0 0. So what are the two options that you have? Either you can place a 1 next to it, and you can form 0 1, or you can put 0 0 to it. So there are two possibilities, right? So 0 0, from 0 0 you can go to 0 1 by adding 1 to the 0. By adding 1 to this 0 you can form 0 1, or you can frame 0 0 again by adding 0. So 0 0 plus 1, you would get 0 1. Okay, put this 1 to this character, leave this character, because we only need of size 2. N equal to 2 is what we needed. All right, so we will not be framing 0 0 1. That's not what we are seeing. We are seeing for the next possible thing, next possible next possible permutation. So from 0 0, either we can have 0 1 or 0 0, because there are two choices available. I can put 0 or 1. If I put 0 or 1, I would get 0 1 or 0 0. 0 0 is again the same thing, so I'll not be putting here. So again, here there are two choices available for me. I can have 1 0 or I can have 1 1, right? There are two possibilities, so I'll just write both of them here. So I can have 1 0, I can have 1 1, right? So at this one I can have 1, so I'll get this, or 0 to get this. Now again 1 0, like 1 1. Now come to this 1 1. Again, this I have two possibilities. What are that? So I can have 1 0 or 1 1. So 1 0 is what I've got here, and 1 1 is itself, so I'll not be doing it. Now this 1 0, this 1 0. So 1 0 plus 1. So this 0 plus 1, this constitutes 0 1, or 1 0 plus 0. This 0 plus 0 constitutes 0 0. So from this you can actually go here. So what is the path? Like, let us raise these particular things. So if we just look into this much more briefly, from 0 0 we visited 0 1, All right, I'll just erase this as well. So from 0 0 we visited 0 1, from 0 1 we have visited 1 1, from 1 1 we have visited 1 0, from 1 0 we have visited 0 0, right? So in this fashion we are able to cover all the possibilities. 0 0 is a possibility, 0 1 is a possibility, 1 1 is a possibility, 1 0 is a possibility. Is there any other possibility that we have left out? No, all the possibilities are covered if you are following this path. 0 0 to 0 1, 0 1 to 1 1, 1 1 to 1 0, 1 0 to back to 0 0. All right, so in this fashion we are able to cover all, we are able to find all these things. So if you assume this is a graph, okay, this is a graph where every node is a possibility, okay, is a possibility. So possibility in the sense the permutations like 0 1 1 0 1 1 0 0, like of size 2, what are all the things that you have. This every node represents a possibility. Now you need to frame for you need to figure out such a path starting from 0 0 such that you can end up getting, you can end up finding all the nodes. Okay, you end up finding all the nodes in the least possible pathway. All right, so least possible pathway, when can that happen? If we do not, if we make sure we are not following these two conditions. What is the first condition? We will not be going through the same thing. All right, we will not be going through the, we will not be using the same zeros or ones or twos, whatever it is, if it's not really required. And will not be making sure, will not be using the same node again twice. If 0 0 I've used now, I'll not be using 0 0 again. That doesn't make any sense. So that is what the things that I need to keep in my mind. So from 0 0 I'll be going to 0 1, from 0 1 I'll be going to 1 1, from 1 1 to 1 0, and then 1 0. I finally covered all the nodes, all the possibilities I've covered. So this is how we'll be doing it. All right, this is how we'll be doing it. So for making sure we are not repeating or we are not visiting the same node once again, what are we going to do? We are going to use some set. Okay, we will be storing all the vertices that we have, like all the possibilities we have encountered so far in that particular set. And if in case that set size reaches the total possibility count, that means we have successfully figured out the path. And in that case, we'll return true, and that means we have got some path, and we will return that particular path or the string. All right, so from 0 0 we have got 0 1, right? From 0 1 we have got 1 1, from 1 1 we have got 1 0, from 1 0, because 0 0 is already there. So we are able to find all the possibilities we have found starting following this path. Now let us erase this and do this particular dry run of this thing. Okay, I'll just erase this particular point. It's going to get much more clearer if you go through the second example. So in the second example, the case is n equal to 2 and k equal to 3, n equal to 2 and k equal to 3. So in this case, k equal to 3, in the sense I've got the freedom to use 0 1 2. Let us start with 0 0. Okay, if I start with 0 0, what are the next possibilities that I have? I can have 0 1, I can have 0 2, or I can have 0 0. 0 0 I'll not be using because it's the 0 0 itself, so I'll not be using it. So from 0 0 I'll be going to maybe 0 1. Okay, 0 1. Now again I have three possibilities. What are there? I can have 1 0, I can have 1 1, I can have 1 2. I'll be choosing 1 0. Let us assume I'll be choosing 1 0. So I'll be coming to this particular thing. Now again I have three choices: 0 0, 0 1, 0 2. 0 0 I'll not be considering because I've already used it. 0 1 is also I'll not be considering, I've already used it. So only thing that's left out is 0 2. So I'll be going with 0 2. Okay, 0 2. And now again there are three choices available for me: 2 0, 2 1, 2 2. So did I use any of them? No, I can freely choose any one of them. So I'll be going with 2 1 1. 2 1. Okay, I'll be going with 2 1. Now what are the again three possibilities that you have here? I can choose 1 0, 1 1, 1 2. 1 0 have already been covered, so I cannot take, and so I have the freedom to choose 1 1 or like 1 2. So I'll be choosing 1 1. So if I choose 1 1, so here, so what are the three possibilities that you have? I can have 1 0, 1 1, 1 2. So 1 0 I've already chosen, so I cannot take this. 1 1 is this itself, so I cannot be take this. Only option left is to go with 1 2. So I'll be going with 1 2. Okay, all right, 1 2. And now again there are three possibilities that are there for me: 2 0, 2 1, 2 2. So 2 0 have already been taken. No, 2 1 has already been taken. Yes, so I cannot use this. 2 2 has not been taken. So I have two options, and among them I'll be choosing 2 2. Okay, if I choose 2 2, so I'll be getting this. So what are the two options that you have right now? You can have 2 0, you can have 2 1, you can have 2 2. But as you already used, as we have already used like 2 1, I cannot take this. Now 2 2 is this itself, I cannot use this. So only option that's left out with me is to use 2 0. So I'll be going from here to 2 0. So what are the options that are left for you to use? 0 0, 0 1, 0 2. 0 0 already been used. No, you cannot use this right here. And 0 1 already been used here. 0 2 already been used here. So all three has been covered. So there is no other option to be covered, and we have already reached the end. So did we cover all the parts, all the points or not? That is what we need to see. Did we cover all the possibilities? Yes, because one possibility, 2, 3, 4, 5, 6, 7, 8, 9. Yes, totally 9 possibilities we have covered, and all of them are unique. So this actually says that we have got the answer, because n equal to 2 means two options are there, and each option has 3 characters to be placed. Can 3 1. So how many possibilities are there? 3 into 3, 9. Total possibilities are 9. And now in this path we have covered all the 9 possibilities. So, and all of them are unique. So that's the reason we have got a required path, and this is the particular answer. Like, this is the particular answer. Great. So this is done by backtracking, because each of the case you're evaluating all the options that are there with you, all the options you're you're evaluating, and you're trying with each and everything. And this is a particularly backtracking. I have not evaluated all other parts. That goes up to a lot of process that we need to do here, we need to show here. I have not showed all those things. I've just showed you the possible pathway that's being formed. So for that, backtracking is there. Backtracking is where is the only thing that we can use, so that we can figure out all the paths going in the DFS fashion. Great. I hope you people understood what are we trying to do. Starting with 0 0, putting all the possibilities, and then trying it out, 1 and 1 and 1 1, finally reaching 2 0. If we reach 2 0, like, we have put all the unique possibilities in our set, and set size got to be 9, and that is the total number of possibilities, maximum total number of possibilities. And now with this we can come to the conclusion that yes, we are able to frame all like, we are able to find all the possibilities. So this is the particular answer. So now we'll return the final path that we have encountered so far. So I hope you people understood. So this is the logic. So let us go through the code now. So going through this code, let us assume we are doing the dry run for n equal to 2 and k equal to 2. All right. So initially we have string path to be string of n minus 1 0. So this means that we will be having a string. So path equal to 0 0. Okay, this is the string that we are having. So this is STL to make sure all the characters of the string to be 0. So we are doing this, and now set visited to make sure we are visiting only the nodes that we haven't visited so far. All right. So it keeps a counter for all the nodes that we have visited, and unique nodes. So once the unique nodes reaches the total possibilities, what are total possibilities? N equal to 2 in the sense 2 blanks, k equal to 2 in the sense there are two choices for each of the blank. So total choices are 4. So once my set size reaches 4, that means I can infer from that I've covered all the unique possible possibilities. So unique possibilities, I've covered all of them. So I'll be returning true. So I'll be doing DFS from 0 0. I'll be doing DFS from 0 0. So how do I do it? So 0 0, starting from 0 0, I have two possibilities, right? I can put 0, I can put 1 to this particular thing, and I can get 0 1, or I can put 0. If I put 0, I'll be getting the same thing again. So I might be doing it. So again, from 0 1, I have two possibilities. I can go with 1 1, I can go with 1 0. Okay. And now again from this, let us assume you are on 1 0. So what are the two possibilities that you have? So once you reach this particular point, you have in your set we have 0 0 0 1, right? You have 0 0 and 0 1 in your set. Now 1 0, you have two possibilities. Either you can go to 0 0 from 1 0, you can go to 1 0 1. Right, these are the two possibilities. I can put 0 0 and get this particular thing. I can put 1 and get but this particular thing. But both of them are already in there in the set. So can I proceed further? No. In this case, my set size is, like, if I add this particular thing in my set, I'll get 0 0 0 1 1 0, and I'll be ending the iteration. And once I end the iteration, I see that I'll be returning false. The reason being, my set size is only 3, but I need to get 4. So I have not got 3. So in this case, I'll be returning false. So that is the reason we'll not be going into this particular thing. Like, once if we go this particular thing, what is the path at that particular point? So path initially is 0 0, right? Path initially is 0 0. And now once we come to this particular thing, we are adding 1. Once if we go to this particular thing, we will be adding 0. But here, because it's returning false, we'll be exempting this. We'll be popping it back. So what is the other option that we have? 1 1. So we'll add it. We will add 1 to it. So we get 1 this. From here, we'll be going here. From that point, we'll be adding 0. So because the next possibility is 0, so in this case, we'll be getting the path, that is 0 0 1 1 0. So the same thing matches here, 0 0 1 1 0, right? I hope you people understood. So we are doing this basic backtracking. So current node is path.substring path.size minus n plus 1. We are taking the substring from that of n size, okay, of n size, and adding that particular possibility that looking out, like int I equal to 0, I less than k. We are adding each and every possibility. Add 0 or 1. In this case, k equal to 2. If it's k equal to 3, we can even add 2. So we are trying to add each and everything, and we are checking if we find that in our set. If we find that in our set already, we'll not be going through it. We'll be exploring another possibility. Like if I add 0 to my like current node, and if it's already there in the set, I'll not be looking into it. I'll be going to 1 and check. So now once I go and check, if I do not find that in the set, I'll be adding that to my set, and then I'll be adding that particular thing to my path as well, and then I'll be doing a DFS on that particular thing. And if it returns true, then I'll return true. If I do not find a true from it, then I'll do the pop back. So in this particular scenario, if you see, from 0 0 we have went to 0 1, from that we have gone to 1 0, and the path in this particular thing is 0 0 1 0, and here it will be giving you a false. So that's the reason we'll pop it back. And also we'll pop it from the current node, and we'll be trying to put 1 because that's the only option left. So from there we'll explore. I hope you people understood. That's what we are doing. This is the backtracking that we are doing. Backtracking, and it's a basic DFS, and we are using a set to make sure we are covering all the unique possibilities or not. I hope you people understood this particular thing. I know it's like I feel the explanation is much more clear, and I've tried to put everything in great detail from the grassroots level. So I think like it must be understandable. If not, please go through the video once again. Alright, so for your references, the code in C++, Java, Python are there in the description. Please go through them. So thank you for watching. Stay tuned, and if there are any doubts, please feel free to comment in the comment section.